Hello, and welcome to the first online lecture for Philosophy 470, Logical Theory. This is a course on Gödel's incompleteness theorem. We will have a number of online lectures for this course. Remember, there's an online component to this course. The online lectures will discuss background material, topics that I didn't have time to cover in class, extending or going over the details of some proof, maybe discussing some homework exercises, and so on. All right, so this is the first lecture, and this lecture is on background material. And what I want to do is I want to make sure that we are all on the same page when it comes to talking about functions. So a function is a way of associating elements from one set to another set. It's a rule or a procedure or an algorithm, just some way for telling us how we can map or associate elements from the set A with elements of the set B. A function, what the function tells you is for every single element of A, which unique element of B is associated with A. And if A is associated with B, then we write B equals f of A. So applying f to A, the outcome is B. Now a bit of notation, A is called the domain of the function f, and B is called the codomain of the function f. Now, you may hear people refer to the range of the function, of a particular function. And what the range is actually a subset of the codomain. And the issue is the following. A might contain lots and lots of elements. B also contains lots of elements. And what the function does is it just associates, or it's a rule for associating elements of A to elements of B. Okay, so there's lots of associations. Now, it very well may be that not necessarily all of the elements of A are associated with an element of B. And similarly, it might be that there are some elements of B that are not the outcome of applying f to any of the elements of A. So there might be some element here, say B prime, that just is not associated via this function f with any element in A. So in that case, B prime would be an element of the codomain, but not the element of the range. So the range of a function f are all, in this example here, would be these three elements. Okay, they're all the elements that are actually associated with some element of A. One other point here, and I said that not necessarily all the elements of the domain may be associated with elements of B. There's a distinction between a total function and a partial function. A total function just means that every single element of A, all the elements in the domain, are mapped to some element in B. For a partial function, that may not necessarily be true. So there might be some elements in the domain that are not mapped to anything. Usually, when you talk about a function, you mean that the function is a total function. But throughout the semester, we will have to be careful to note when functions are total and when functions are partial. All right, so let's move on to some examples. So here's a sort of very abstract example. Suppose we have this set A and the set B. A contains three elements, A, B, and C, and B contains four elements, 1, 2, 3, and 4. So the function definition says A gets mapped to the element 3, B gets mapped to the element 2, and C gets mapped to the element 1. Okay, so this is just an abstract definition of a function, or a definition of an abstract function, I should say. Here's a more concrete example. F is a function, so the domain is this set N, and the set N is all the natural numbers, the counting numbers starting from 0. So 0, 1, 2, 3, and so on. So f is a function that maps a natural number to another natural number, and it does so by squaring that number. So f of 0 is, of course, going to be 0 because 0 squared is equal to 0. F of 1 is equal to 1 squared, which is 1. F of 2 is 2 squared, which is 4, and so on. The next example is the successor function. So this also maps natural numbers to natural numbers. And all it does is it sends every natural number to its successor, to the next element in the sequence. So s of 0 is equal to 1, s of 1 is equal to 2, and so on. Finally, a little bit more complicated function, this function p. And what this does, this is a new piece of notation that you may not be familiar with, n cross n. So this is the set of all ordered pairs. So if I have two sets, A and B, I can define a new set, A cross B, which is the set of all ordered pairs, the set of all pairs A and B, such that A is an element of A and B is an element of B. So n cross n is the set of all pairs where each component of that pair is a natural number. All right, so all this does is it takes pairs of natural numbers, and the output is going to be the sum of those two numbers. So p of 1, 2 will be 1 plus 2, which is equal to 3. P of 2, 7 will be 9, and so on. All right, so these are all examples of functions. The first one's kind of abstract. The last three are concrete functions. We will study these functions actually in a lot of detail throughout the semester. But these are all examples of functions. Okay, so I want to conclude this lecture by talking about a few special types of functions. So the first type of function that we'll be studying is a surjective or onto function. And this is a function that satisfies a special property. And what the property is, so suppose we have a function from A to B. A function is said to be onto if every element in B has a preimage. So there has to be, so if I take any element in B whatsoever, I have to be able to find some element in A such that F associates A with B, such that B is equal to F of A. Okay? Using the notation I introduced a little bit earlier, a function is going to be onto or surjective if the codomain is equal to the range. Because the codomain is this entire set B, and the range are all those elements of B that are associated with some element from its domain. Okay, so this is an onto function. If we look back to our the examples we discussed earlier, here's a function, and it associates with A the element 1, B the element 3, and C the element 3. So we have A, B, and C, 1, 2, and 3. So A gets mapped to 1, B also gets mapped to 1, and C gets mapped to 3. So we can see that this is not an onto function. So is this onto? Well, the answer is no. And why is this not onto? Well, here's an element 2 here. The element 2, it's an element of the codomain, but there's nothing in the domain that maps to 2. What about this function right here? So here we have, again, A, B, C, 1, 2, 3. And we see A is associated with 1, B associated with 2, and C is associated with 3. And it's easy to see that this is, of course, onto, because every element in the domain, there's a preimage, there's some element in the domain that's mapped to it. So every element in the codomain has a preimage. So what about a more concrete example, the successor function? So is the successor function onto? Well, at first you might think that the answer is yes, so you kind of run through some examples. You see 2, 3, 1, 2, 3, and so on. Those all have, so 1 s of 0 is equal to 1, s of 1 is equal to 2, and so on. But what about 0? So 0 is an element of the codomain. What element is mapped to 0? Well, since the domain is just all the positive natural numbers, including 0, there's nothing that maps that can map to 0. So this is not an onto function. And what about the addition function? So let's think about this. Is it the case that if I take any natural number, that natural number, I can find a pair of natural numbers. So for any natural number, can I find a pair of natural numbers, let's say m1 and m2, such that m1 plus m2 is equal to n? Well, a moment's reflection, hopefully it's coming to you now. Remember, n includes 0, so I could just take the pair n0. So n comma 0, p of n0 is always going to be equal to n, because n plus 0 is n. So for every natural number, there is always going to be at least one pair that is mapped to that natural number. Now, of course, this is a nice example, because there are going to be lots of pairs that get mapped to a particular natural number. So consider, for example, 3. So we have 3, 0 is mapped to 3, but also 1, 2 is mapped to 3, and 2, 1 is. But being surjective just means there has to be at least one. The next property is the property of being injective or one-to-one. And what injective means is that if we take two distinct elements of my domain, those must get mapped to two distinct elements of my range. So if x is different from y, so this is x and that's y, then f of x has to be different from f of y. Let's look at some examples. What about this function right here? So we have a, b, and c. 1, 2, 3. A is associated with 1, B is associated with 2, but C is also associated with 2. Okay, so is this function one-to-one? Well, no, because B and C, B is different from C, but f of B is equal to f of C. They both get mapped to 2. What about this next example right here? So again, we have A, B, C, 1, 3. And we have A gets mapped to 1, B gets mapped to 2, and C gets mapped to 3. And it's easy to see that this is, of course, one-to-one. What about the successor function? Is it the case that if we have two natural numbers and they're different from each other, then s of n is different from s of n? Well, if n is different from n, if you add 1 to n and you add 1 to m, those result in different numbers. So indeed, the successor function is one-to-one. Finally, we will say that a function is bijective if and only if it is both injective and surjective. So we might also say it's a correspondence. This concludes the first online lecture. The goal was simply to introduce or remind you of some of the basic definitions of what a function is or properties of functions. I hope you enjoyed it. If you have any questions, please send me an email or talk to me in class, and I look forward to the rest of the semester.